All right, welcome. Today we're going to crack the code on something that sounds, well, pretty intimidating, right? Nuclear equations. But here's the secret, it's all governed by a couple of super simple rules. Seriously, you don't have to be a physicist. If you can count, you can do this. So let's just dive right in.
So let's start with the big question. What happens when the very core of an atom changes? I mean, we tend to think of atoms as these solid, permanent building blocks, but their nucleus can go through these incredible transformations. It's called a nuclear reaction, and it's where the number of protons or neutrons actually changes. The atom's whole identity gets rewritten. It's basically modern-day alchemy.
You know what, let's treat this whole thing like a detective story. The scene of the crime, the atomic nucleus. This is a place where one element can literally just become another. Our job is to figure out how it happens and what new things get created along the way.
Okay, so to solve any mystery, you've got to know who the players are. In the world of nuclear reactions, we've got a whole cast of subatomic particles. These are our usual suspects. They're either already in the nucleus, or they're the things that get shot out during a reaction.
Here's our lineup. Of course, you've got the protons and neutrons. They're the main residents of the nucleus. Then you've got the particles that often get ejected. There's the alpha particle, which is really just a high-energy helium nucleus. A beta particle? That's a high-energy electron. Then you have the positron, its antimatter twin. And finally, gamma rays, which aren't really particles at all, just pure bursts of energy.
Let's just pause on that positron for a second, because it's fascinating. It's the most common piece of antimatter you'll hear about. It's identical to an electron in every way, same mass, everything, but it has a positive charge instead of a negative one. And here's the really wild part. When a positron runs into an electron, they completely annihilate each other. Poof! Their mass gets converted entirely into pure energy, usually in the form of gamma rays.
All right, now that we know our suspects, we need the laws that they have to follow. And luckily for us detectives, there are just two. Two simple, unbreakable rules that apply to every single nuclear reaction out there. These are the laws of nuclear conservation.
And here they are. It's this simple. First, the total mass number. That's the top number. The total count of protons and neutrons. It has to be the same before and after, always. Second, the total charge. That's the bottom number, the atomic number, which is just the protons. That also has to be the same on both sides. And that's it. The whole thing just comes down to simple addition and subtraction.
So it's time to put those detective skills to the test. Let's take those two rules and apply them to a real case. We're looking at a reaction where an alpha particle hits a magnesium-25 atom. Our mission? Identify the mystery product.
Okay, here's our equation on the screen. Magnesium-25 gets bombarded by an alpha particle. The reaction spits out a proton and, well, something else. Some unknown particle or nuclide. Our whole job right now is to use our rules to figure out exactly what's hiding behind that question mark.
Let's start with rule number 1. Conserve the mass number. So we're just looking at the top numbers. On the left side, we've got 25 from the magnesium plus 4 from the helium. That gives us a total of 29. Now on the right, we have 1 from the proton plus our unknown mass number, which we'll call A. So 29 equals A plus 1. A little quick math tells us A has to be 28. Simple.
Now for rule number 2, conserving the charge. Let's look at the bottom numbers. On the left, we've got 12 from magnesium plus 2 from helium, for a total charge of 14. That means the right side has to add up to 14 too. We already see a 1 from the proton, so our unknown atomic number Z must be 13.
And there we have it. We have the complete identity of our mystery particle. It's got a mass number of 28 and an atomic number of 13. So all we have to do is check our periodic table. Find the element with 13 protons, and we've got our answer. It's aluminum. Our mystery product is aluminum-28. Case solved.
Now, balancing these equations isn't just some boring textbook exercise. These exact same principles were the key that unlocked some of the most massive discoveries in the history of science. Let's take a look at a few famous cases where these simple rules were absolutely everything.
I mean, think about it. This simple balancing act was the key. When Marie Curie discovered polonium, she was actually observing and documenting a natural nuclear reaction. When Rutherford created the very first artificial element, he had to rely on these rules to even understand what he'd made. And maybe most impressive of all, James Chadwick discovered the neutron, just by balancing a nuclear equation and realizing there had to be some unknown neutral particle in there to make the numbers add up. So the big takeaway here is that all this stuff, the transformation of matter, the release of incredible energy, the creation of brand new elements, it all follows these two simple rules. It's just a beautiful reminder that underneath some of the biggest complexities in the universe, you can often find this elegant simplicity. So I'll leave you with this question. What does it really mean that the universe's most profound power is governed by rules we can solve with just basic arithmetic?